there you go. Okay.
I'm worried for one.
So this is the triangle I just asked second period today. Hey, create a side-side angle for me. And they created angle A is 20 degrees, side A is 5 in length, and side B has a length of 7. So this is an angle side-side, randomly created by second period. And so odds are, if you were to just randomly create an angle side-side, you would get a triangle similar to this one. So in order to show you why this is ambiguous, let's construct this triangle. Now you could get like a protractor and a ruler and maybe get like little pieces of spaghetti and cut them to the lengths and try and actually build this triangle. I said GeoGebra, bam! Okay? So I'm going to start by making a side of length 7. 7. There we go. Grab my angle tool. I'm going to construct an angle on that side of 20 degrees. Right? This here is technically not angle B. That would be angle C. Yeah. I do not know what the length of this side is, so I'm going to draw a ray there so that it goes forever and ever and ever. But I do know what the length of the last side is. It is 5. So I'm going to make this a length of 5 right there. So the question becomes, is this triangle even possible? Because what you learned in geometry was angle side-sides never happen, right? Side-side angles. Now they do sometimes. So we are looking at a triangle where this angle right here is 20 degrees. This side, adjacent side, that is side B, is length 7. And then this side over here that I'm swinging around is length 5. Does a triangle exist with an angle 20 degrees, an opposite side of 5, and an adjacent side of 7? Yes, it would be this triangle right here. So what's the confusion?
Sometimes there's 2 answers.
What? Whoa. So here's a triangle with an angle of 20 degrees, an adjacent side length 7, and an opposite side length 5. Here's a totally different triangle. Still with an angle of 20 degrees, an adjacent side of 7, and an opposite side of 5. So this is a perfect example of a side-side angle where if I were to say, solve this triangle, find for me all of the angles and sides of a triangle who has an angle of 20 degrees, an opposite side of 5, and an adjacent side of 7. And how many solutions would this triangle have? It would have 2. And so you would have to find both of them. You'd have to solve this triangle right here, and then you'd also have to solve this triangle right here. Does that make sense? Now, does that mean all side-side angle triangles have 2 solutions?
No.
No.
Yeah.
No.
How would you do it 2 different ways?
This triangle right here, you'd have to solve this one, and then you'd also have to solve that one.
Wait, are you talking in terms of like
That's what we're
if you
here to
get a
learn.
problem and you can make 2 things?
Right. So the question now is, okay,
The opposite side.
let's go one question at a time. My question was, do all side-side angles have 2 solutions like this?
No.
No.
And the answer is no. So let's change this length right here. Right now this is a length of 5. What would you like to change the length to?
1.
Let's make it a length of 2. What if this opposite side actually had a length of 2?
It wouldn't work.
How many solutions does this triangle have?
0.
None. That triangle right there is impossible. That is a triangle that has an angle of 20 degrees, adjacent side 7, opposite side 2. So if I were to say, solve this triangle, you would have to say, no solution. No triangle can exist. This leg is just too short. That's a great
But
question.
If it can exist, is there 2?
What if this length right here was
12.
12? Evan says 12. Let's make the opposite side a length of 12. Does this triangle exist?
No.
Bam! There's one solution. Where's the second solution? There isn't one. So here's an example of a side-side angle that has one solution. Right? That's it. That's the only solution. Angle 20, opposite side 7, or adjacent side 7, opposite side 12. So the question becomes, alright, I just showed you an example of a triangle that has two solutions, a side-side angle that has no solution, and a side-side angle that has one. How in the world do you tell the difference? Why was this one right here obviously one solution?
It was longer.
What's longer?
It was longer than the other side.
The side opposite your given angle was longer than the adjacent side. Do you think it's at all possible to get one of those two solution scenarios where this side's longer than that side?
No.
No. So there's a criteria right there we're going to want to remember and memorize. If the opposite side is longer than the adjacent, there's one solution. What if it's the same length?
There's one solution.
Still one solution. So what if I make this a length of 7 exactly? Okay? Here's one solution, and then when I try to swing it around to get another solution, it hits right, that's not a triangle, so yeah, you're right, one solution. So here's what I would write down. And we want to make this as general as possible. So what I would do in your notes is I would draw a triangle, label this A, label this point up here B, label this one C. So this will be lowercase b, lowercase a, lowercase c. If A is greater than or equal to B, then there will be one solution. That makes sense, right? If the opposite side is longer than the adjacent side or equal to the adjacent side, there will be one solution. So in this example, the adjacent side was length 7. So if I make this side length 7 or larger, one solution. Now what happens when I make this length shorter than 7, like 6? Here's a solution. Right here. But then there's another one here. But then there's the problem. Okay, so clearly, if the opposite side is shorter than the adjacent side, there could be two solutions. But there's a limit to how short it could be. Because if I go too short, like 1, aw, poor guy, not even close. Right? So what if it's, let's try 2. Still too short, no solution. Let's try 3. Well, now that is long enough. There's a solution, and here's another one. So if the length was 3, there would be 2 solutions. Let's try 2.5. Here's a solution. And here's another one. 2 solutions. I'm just going to try a random number here. I'm just thinking of this number off the top of my head. 2.3941411003. Just made that up randomly. Is this one going to be too short and you have a triangle with no solution? Or is it going to be so long that it crosses it twice and makes 2 solutions? Oh, by golly, that length is just perfect to where it touches the other side but then comes away from it again. So how many solutions does this side-side angle have? One solution. It's the perfect, ideal length. And it creates one solution, and not just one solution, that is actually guaranteed to be what type of triangle? That is a right triangle solution. Guaranteed that this leg is just perfectly long enough to where it can touch that other side once and only once. Then what's true about tangent lines to circles? Aren't they perpendicular to your radius?
Yeah.
Right? Isn't this leg that's swinging around here essentially drawing a circle for us if I trace this point? And isn't that third side tangent to the circle? Pretend.
That's awesome. That's awesome.
Right? And so, well, for some reason the scaling is off on the grid. Just pretend. It is a circle, it just doesn't look like one. So because that third side of the triangle is tangent to the circle, doesn't this angle right here have to be 90 degrees? Yes. So, Alex, what's up?
In geometry, didn't we learn some sort of inequalities that for an obtuse triangle, it's a squared plus b squared is greater than c squared?
Yeah, but that's not going to matter here because we don't know all three sides. We only know these two sides. So without knowing that third side, we're not going to be able to test whether or not it's obtuse using the Pythagorean corollary. Okay? So here's what we've discovered. If the opposite side is longer than the adjacent side, how many solutions? If the opposite side is longer than the adjacent, one solution. If the opposite side is this perfect ideal length that it touches tangent, how many solutions? One, and specifically it's a right triangle. If the opposite side is any length larger than this ideal length here, but shorter than the adjacent side, how many solutions will there be? Two, right? If I make this leg longer right now than what you see here, but still shorter than the adjacent, it will cross that triangle, that third side twice. Agreed?
Yeah.
Right? If I make this leg shorter than that perfect length you're looking at right now, how long will it be? How many solutions will there be?
Zero.
None. So here's what we've discovered. Okay? There is some magical length. I don't know what it is. Right now I'm going to call it star. Or whatever. I don't know. Make something up. What should we call it?
Yeah, I like that.
Star sounds good? Alright. How many pointed stars? 7, 9, 5?
5.
6.
5?
Make it fancy, do 6.
Okay, we'll do 5. If the opposite side A is shorter than B, but is bigger than whatever this magical length is, we're calling star, how many solutions will there be? 2 solutions. If the opposite side is equal to this magical length star, how many solutions? 1, and not just that, it's a right triangle. We'll figure, it's that perfect length that makes the segment touch the other side perfectly perpendicular to it.
Star is less than A and
If A is larger than star but less than B, there will be 2 solutions. And we'll discover what star is in a little bit. And then if A is smaller than star, no solution. Agreed. So now the question becomes, what is star? Right? Well, let's think about this. If the opposite side is the perfect length, star, then what type of triangle do we have? Right triangle, specifically where this angle right here is our 90-degree angle. Somebody solve for star in terms of A and B. Woo.
Okay, sine
Good. Sine A equals star. Oh, that's not a star. Star over B. So therefore, star is B sine A. That is how you determine what that perfect length is. So for our example we were doing, what did I do on my calculator to come up with that random 2.39 number? I did 7, which is the adjacent side, times the sine of 20 degrees. 2.3941410003. That's how you come up with that perfect length. That was an angle of 20 degrees and adjacent side is 7. So I type 7 sine 20. That's the perfect length. If my opposite side is larger than that but smaller than 7, 2 solutions. Okay? That's the key. So I would go back through in your notes and don't write star. Call this B sine A. So here's what we have. And be careful because any particular example, the sides might not be A and B. They could be B and C or C and A, right?
Is it always sine though?
Always sine.
So they'll always give you that.
Somebody coming in? Yeah. Okay, what we're learning about side-side angle situations. So an angle, the side opposite that angle, and any side adjacent to that angle. Right? Side-side angle. A is always the side opposite the angle you know. B is always one of the sides adjacent to it. If your opposite side is larger than your adjacent, there will be one solution. Okay? If the opposite side is shorter than the adjacent, then you got to determine, is it too short? So you figure out what B sine A is. If the opposite is between B sine A and B, two solutions. If it's equal, one right triangle solution, and if it's too short, there are none. Now, I don't want to ruin this any further for you, but everything we have just analyzed is only true if A is acute. All of this is true if A is acute. What happens if that angle is obtuse?
It's opposite.
So let's create an example with an obtuse angle. Let's visualize this. What's your favorite obtuse angle?
137.
137? That is weird.
97.
97 is not obtuse. Yeah, it is. Just testing, yeah. Just testing.
I thought I would cry. That was actually cute.
I was hoping it would have been funny, but yes. Oh, sure. Okay. All right, so let's create a line segment of length 4. Okay? How many solutions can this triangle right here have? None. Impossible. Let's try. Let's make it length 7.
Wait, what's the length of the adjacent?
Yeah.
It's like 7.25 or something like that. How many solutions here?
0.
None. What has to be true? This is a much. It just has to be bigger, and that's it, right?
Yeah.
If this opposite side is bigger, there will be how many solutions?
1.
1. If it's shorter, there will be how many?
None.
0, and that's it.
Oh.
So the case where the angle is obtuse is much, much easier, right? If A is obtuse, then if A is greater than B, one solution. Otherwise, if A is less than or equal to B, none. So that's what you have to memorize. Now, hopefully, you know me, I'd rather you understand all of this rather than just memorize it. But worst case scenario, you just memorize all that. So how do we approach a problem? First of all, I say, solve this triangle. The first thing you got to do is look at it. Look at what information has been provided to you to determine what method you're going to use to solve it. If I'm giving you angle side angle, you're just going to use law of sines, piece of cake. Right? If it's side angle, you have to first identify, oh crap, this is a side angle. Right? You always got to remember those, you got to be really, really careful about them because they can make an angle side out of you. First word humor. All right.
Okay, Dalton, that's the first time. Not funny. I thought it was pretty
I thought it was very good.
It's just a good way to remember. You gotta be careful, right? So,
You already met me. You were outside my friend's room. Okay, anyway.
are you done?
Yeah.
Nice.
Okay. So if it's a side angle, you have to first identify. Oh no, side angle. How many solutions could it have? And this is how you determine it. First thing is the angle they give me acute or obtuse. If it's obtuse, if the opposite side is longer than the adjacent side, one solution. Otherwise, no solution. If the angle is acute if the opposite side is greater than or equal to one solution. If it's between the adjacent side and this perfect magical value, two solutions. If it's equal to one right triangle solution, so you can use SOHCAHTOA. And if it's less than, no solution. So that's the process you have to go through. So that helps you identify how many solutions. Then you actually got to figure out how to find all of the solutions. And one of the things that messes students up the most is actually drawing the picture. Right? Here, let me show you an example of how students mess this up. Because they see me all the time drawing my picture like this. I give you angle A, and side B, so I draw my picture so that angle A is in the bottom left, the adjacent side that's given to me is along the bottom, and then the opposite side is over here. So this side is swinging like this. I do not know the length of C, I don't know the angle B or angle C. So you swing the side around like this, right? What if, however, you go to approach a problem? Let's create a triangle right now. Let's create one. What angle do you want to know, A, B, or C?
B.
Let's say angle C is 37 degrees.
No, can we make it 36?
36.
Can we just keep it? It's
Make
fine.
it 36.
36.
42.
42. 42.
So angle C is 38 degrees.
Compromise.
Oh, what now? Fine, 36 degrees.
What about 42?
Angle C is 36 degrees. Why? Because we know 36. It's something we've memorized on unit circle. Steve, you should see that face though. That was great.
I was like, what?
I don't know why he wants 36. Why does he want 36?
Look, 42.
Oh, 36 is in the homework? Don't give me one that's in the homework.
Why would you tell him that? It takes your own number.
Side C is what?
Unknown.
Well, then it's not a side angle one.
You know side B.
12.5.
So we'll say side C is 22. And so then pick one, A or B.
B.
Hey.
Side B is what?
4.
2. Okay. How many solutions?
None.
1.
1.
Okay? Listen. The opposite side is bigger than the adjacent. 1 solution. Right? That's a piece of cake right there. Try to create one that has 2 solutions for me.
2.
32. Okay, so let's suppose this is the question. You identify it's a side angle, right? Opposite side, adjacent side angle. You then notice, hey, this side is shorter than, the opposite side is shorter than the adjacent. Could be 1 solution if it's the perfect length. Could be 2 solutions if it's between the perfect length and 32. Could be no solution if it's shorter than the perfect length. So the next thing I do right now is calculate what is that perfect right triangle length. So in my calculator I say, what is the adjacent side, which is 32, times the sine of the angle, which is 36. 18.8. If the opposite side were 18.80912.807 in length, this would be 1 solution. Specifically, it would be a perfect right triangle. If the opposite side is shorter than this, how many solutions?
1.
0.
0, sorry.
0.
If the opposite side is between this number and 32, how many solutions will there be? 2, which is exactly the scenario we have right here. So now, what I would recommend is not only draw the picture, I recommend doing this. Draw the picture. One picture that you can see that side swinging to see both triangles, then draw the 2 triangles separately, because you got to solve both of them as if they're 2 separate problems.
I thought if A was greater than B side, A was no solution. Did I get that wrong?
That's wrong.
That's wrong.
If A is greater than B sine A, right here,
Yeah.
but is less than B, 2 solutions.
Oh, I
If A is less than B sine A, no solution. Okay. Where'd it go? There it is. Okay. Now, what I would always recommend, draw your triangle. I can't. I'm not satisfied. There we go. That's good enough. Okay. I would always make the bottom left triangle the one that's given. So I'm going to call this angle C. So then this is side C. And I'd make the adjacent side they give you the bottom. So that means this has to be angle B. This right here has to be angle A. I would always try to stick to that convention. Okay? Because if you do it like this right here is your swinging side, and which point is it swinging around, A or B? It's swinging around A, so it swings around like this. Okay? Make sense?
Yeah.
So your other potential triangle would be like right here. So it'd be this triangle here. Okay? Now here's the problem I see a lot of students do. They label the triangle differently. Maybe they just always label it ABC like this. How many of you usually do that? You just always label it ABC. That's fine. You can do it that way. Now, this is 36 degrees. This is 32. This is 22. Where's your swinging side?
On the right side.
It's this one, and it's swinging around this point. Like this. But most likely, what are students who draw the triangle like this going to try and do? They're going to try and swing this thing here, hence shortening 32, which shouldn't happen. It's amazing how drawing the picture like this and then trying to create your two triangles from this side will result in wrong answers, just from drawing the picture wrong. You can do it like this, but now you've got to, I don't even know, your other triangle is going to be like right here, maybe? How many would not have drawn those two triangles if they labeled their triangle like this? Right? So, let's go ahead and do this problem. Let me start again from the beginning and show you how I would recommend you do it. Let's start with, I'll draw it in blue. Okay? So I'm going to call this angle C, call this angle B, this will be A. So this is 36 degrees, this is 22, this is 32. So then where's the second triangle going to be? I'm going to do that again. I'm not happy with my drawing this period. No. So there, we'll just do it like this. There, good enough. That's fine. So there's C. Don't talk about electrons in my math class.
Not me. That's her wife right there.
I really want to be able to teach and have people feel like they're paying attention to me. Okay, so there's your triangle. Now that is not the only triangle that can have that arrangement. You could also have, man, I just cannot draw this very well. There, that's good enough. Okay? So there's two triangles that can have a possible 36 degree angle, opposite side 22, adjacent 32. There's the triangle in blue, and then there's the triangle in red. Huh? The opposite side is always the swinging side, and it always swings around where it connects to the other number. They tell you it's 22. They tell you C is 22. So whatever side is opposite angle C has to be 22. Because they said so. Right? Does that make sense? Okay. Now, here's what I want to point out. We have two triangles to solve. The red triangle and the blue triangle. But for now, I want to focus on this green triangle here. Because what is true about that triangle? It's isosceles. Because these sides are the same, what has to be true about these angles? They're the same. So then, what is going to be true about the two possible values of angle B? whatever angle this comes out to be, the red one will be supplemental to it.
Wait, they don't.
They'll add up to 180. So whenever you find the blue angle B, you subtract from 180 to get the red angle B. Okay? So once you feel like you got an idea of what these two triangles look like, I would draw them separate. We've got blue triangle.
What do they mean?
So here's 36 degrees. And then we have the red triangle. So here's the two triangles we're going to need to solve. And what do we know about these triangles right now? This angle B and this angle B will add up to what? 180. Okay? Now, what are you going to use to solve these?
Reciprocal.
Look at what you have. You have a side angle opposite pair, and you have another side. You're going to use law of sines, right? According to law of sines, the sine of 36 degrees divided by 22 is going to be equal to the sine of B divided by 32. That's enough information to solve for B. Now the problem is, angle B.
Yeah, but are you solving?
Are you talking blue one or red one? That's what I'm going to get to. Okay. In order to solve for angle B, we are going to have to use what function? Arc sine. Now remember everything you know about arc sine. It can only give us angles between what and what? No.
No,
Negative pi halves.
Negative 90 to positive 90. So therefore, it's only going to give us an acute angle back as an answer. One of these B's must be acute, the other one must be obtuse. Because they add up to 180. So which one of these is it going to give me? The acute one, which I have drawn in blue. I will then subtract it from 180 to get the obtuse one. Does that answer your question?
You find out which one's acute, which one's obtuse when you're drawing it like.
Yeah, you're just going to draw it so that one of the angle B's is acute and the other one's obtuse.
Does it make a difference?
Doesn't matter, but when you go to use law of sines, it's going to give you the acute angle B.
Well, could you say
For
that
sure.
you wanted the acute one to be the red triangle?
Yeah, I don't
Okay.
care what color you use.
Is there like any particular reason why you put the sides on the top and the sides on the bottom?
No,
Or just
because technically law of sines actually has this.
Well, yeah.
But it doesn't matter. So in my calculator, I'm going to type the arc sine, the inverse sine of 32 sine 36 divided by 22. So what is the inverse sine of 32 sine 36 divided by 22? So I get angle B is 58.76 degrees. Okay, so this angle right here, 58.76 degrees. So now, how do I find the red angle B? I say 180 minus that. And I get 121.24. Now, how did I know the blue angle B and the red angle B were going to be supplementary like that? Because when you have them in the same picture, you can see they create an isosceles triangle, right? One of them is guaranteed obtuse, one is guaranteed acute. I should have just drawn it. Why didn't I construct this one? What's our adjacent side length? 32. What was our angle? 36. So let's get a ray here. Now I'm going to do something a little bit different than you saw before. This is a very common technique. I'm going to make a circle. What is the side of the opposite leg? So I'm going to make a circle of radius 22. And then I'm going to mark where this circle intersects this ray. And then I can erase the circle. I can even erase the ray now. And I can actually create two triangles. There's this triangle. Is this the obtuse or acute? That's the obtuse. So does that mean this is guaranteed to be an acute triangle, the second one?
Yep.
Well, that angle is guaranteed to be acute. This angle could still be obtuse.
Yeah.
I mean, that doesn't matter.
But
But this angle here,
angle C.
well, yeah. The GeoGebra labels these automatically. It's not going to match the label
Well, yeah,
we're doing.
That angle.
But there's the two triangles. You can clearly see this isosceles. So these angles are supplementary. And there's your two triangles right there. Okay? So now that I have angle B, I can easily find angle A, yeah? To find angle A, in blue, I can say 180 minus 36 minus 58.76. So that's going to be 85.24. So that's the blue angle A. 85.24.
Like subtracted the red angle B. Like so take out 36 from that angle. Like the 89.24.
Okay.
Is that important?
Yeah, I think so. And then the red angle A is going to be 180 minus 36 minus 121.24. And we get 22.76. And then the only thing left is to find side A. How do I solve for side A? Use law of sines. So we're going to have in blue A over the sine of 85.24 equals 22 over the sine of 36. So 37.3, and then in red, alright, I guess we're done.